Quantum computing has been all the rage nowadays. Ever since Google revealed that they reached quantum supremacy, everyone's been jumping on the quantum computing train. However, people always ask me the question, what makes quantum computers so much better than classical computers? I thought it would be useful to look at a specific quantum algorithm that I've been replicating and compare it to its classical counterpart to really see the difference. The algorithm that we're going to be looking at today is the Bernstein-Vazarani algorithm. So there was a specific problem that inspired this algorithm. So imagine we have a black box, and inside we put a number. The computer has no idea what the number is, but it wants to create an algorithm to solve it. For example, let's take the number 1001, which is 9 in binary code. We put it into this black box, and we want to feed it to a classical computer to solve it. The classical computer makes its first guess on the algorithm. The first guess is always going to be leading zeros following by a 1 as the last bit. So in this case, our first guess is going to be 0001. The algorithm then compares the secret bit string that we put in the box with its first guess. To do this, it performs AND operations on the bit string. Whenever there's a 1 in the same place, the computer takes this and outputs the number 1. That means that the algorithm successfully found where 1 is in the bit. So if we take the bit string in the secret box and the bit string that we made, we can compare them and see that both of them have a 1 as their last bit. The algorithm does this for every single bit in the bit string. So the next guesses are going to be 0010, 0100, and then finally 1000. And then by the end of it, the algorithm would have found the secret bit string, which is 1000. This seems pretty efficient, and it's a pretty good method to find the secret bit string. However, for as many bits as there are in that bit string, the classical algorithm will take that many steps. So say we have a bit string with 1,000,000 bits, the classical algorithm is going to have to perform 1,000,000 steps just to find that secret number. Now, if we use a quantum computer to solve the exact same problem, we're going to see a skyrocket in the efficiency. The algorithm specific to this problem is called the Bernstein-Vazarani algorithm. What we want to do first is we want to initialize a qubit for every bit in the string. So taking our 1001 example, we would have 4 qubits for that string. Then we're also going to have to add 1 extra qubit, and we'll get to that later. And then on top of that, we want to have 4 more classical qubits to input our measurements in. After this, we want to apply a Hadamard gate to the first 4 qubits. Doing this puts them all in superposition. And as for the last qubit, we want to put it through a NOT gate and then apply the Hadamard gate. At this point, the first 4 qubits are going to be in superposition denoted by ket plus. And as for the last qubit, it's going to be in superposition of ket minus. Now for the fun stuff. The algorithm then goes through a series of C-NOT operations. A C-NOT gate is a controlled NOT gate. Kind of how the classical algorithm operated an AND gate whenever it found a 1, the quantum algorithm operates a C-NOT gate wherever it finds a 1, and targets it to the extra qubit at the bottom. Without diving too much into the math, this qubit at the bottom is crucial for this circuit to work. This target bit ends up going under something called phase kickback. During this phase kickback, there's an extra minus sign that results from the equation after applying an X, an H, and a C-NOT gate. This minus sign then gets put back into the control bit. We then apply another Hadamard gate to all the qubits and then measure their values and store them into the classical bits. After that, we know which bits are going to be 0 and 1 based on their superposition of either ket minus or ket plus. Ket minus indicates that a 1 is going to come out of that superposition, and a ket plus indicates that a 0 will come out of it. The resulting values in the classical bits form our original secret bit string. See, the quantum algorithm actually performs all of these operations simultaneously. This means that the algorithm only has to take 1 step to solve this problem. No matter how many bits are in that bit string, be it 3 or 1,000,000, it is always going to take 1 step. The Bernstein-Vazarani algorithm is just one of the algorithms that prove how much stronger quantum computing can be over classical computing. Although it's not so advanced or useful, it is an important proof that quantum computing has a significant advantage over classical computing. Anyways, that's all for today. I hope you enjoyed this video, and I hope you learned a little bit about the Bernstein-Vazarani algorithm. Make sure to stay tuned for more quantum projects in the future. Bye for now!